So we will look at, in today's session, we will look at the traveling salesperson's problem. Now this problem is also, this problem can also be solved, using the dynamic programming approach. Now the traveling salesman problem is one of the graph problems where we have set of vertices and set of edges. Actually in this graph of traveling salesperson, all the vertices can be visited from every other vertex. So if you look at the graph on the left side, what you're going to see is all the edges from every vertex to every other vertex. And this problem is that we start with the first, vertex. Usually, if you take an example of a postman, starts from the post office and he has to deliver all the letters. So he visits each house. In this case, they are vertices, and then come back to the post, ultimately at the end, come back to the post office. So what we have to find is the path which the postman takes or which the traveling salesperson takes. And this path has to be, since the problem is optimization problem, so this path should be least cost path. So it's the minimization problem. Now, if we look at the graph on the right hand side, it's nothing but it's a simple, the simplified version of the graph on the left hand side. The left-hand side graph has all the weights on the edges, which are nothing but cost. It can be a traveling distance. It can be a time taken to travel between two different vertices. So the simplified graph just has edges, vertices and edges, and its cost of edges is represented using a graph adjacency matrix, which you can see on the left rightmost side, where we have 4 rows and 4 columns, and this row and the column represent the edge. So we have, for example, if we look at this cell, which is at 1, 2, this represents the edge cost of the weight of the edge between vertex 1 and vertex 2. Now, even in this graph, in this adjacency matrix, you can find that there are no self loops. So we don't consider in this design analysis of algorithms, we don't actually consider any node to have a self loop. So whatever problems we have seen earlier, also graph related problems, we never considered the self loop. So that is the reason the diagonal elements in the adjacency matrix, that is 1, 1, 2, 2, and 3, 3, 4, 4 are all zeros. Now, since this problem is a minimization problem, so what we have to do is we need to find the cost of visiting every vertex and coming back to the starting vertex. So it's actually, we say that the cost of the graph is so much, that is minimum cost it takes to visit all the vertices. Now here, what we start is, since it's a dynamic programming approach, what we do is at each stage we have to make a decision. In this case, suppose we start with the vertex 1, though you can start with any vertex, doesn't matter, but usually it's the vertex 1 is the starting point. So when we start with vertex 1, what we need to do is we need to look at the adjacent vertices of least cost. So once we find that, then from that vertex, which gives us the least cost path, from that vertex we need to again find the other vertices which gives us the least cost. So this process has to continue. So what strategy we use is, obviously even in the dynamic programming, what we do is we will use a formula here, G of I comma S. Now here I is nothing but the vertex. initially it's the start vertex, and S is a subset of other vertices. S is the set, actually it's a set of other vertices. It will be a subset of the entire the vertices what the entire graph has. So if we start with 1, then the subset is we have to find 2, 3, and 4 is the subset. So this equation, what we derive is, if we have to find a path from I, xi, to the other vertices, all the other vertices in the graph, then it will be the minimum of ci comma j. Now c over here is nothing but the cost of the edge from I, vertex I to vertex j, plus g of j comma, then again subset of those vertices. So this is the general formula. You will, it will be clear when we try to apply this formula to this problem. So let us proceed further. So let us consider the same graph, and we have this adjacency matrix. So what we have is the formula over here on top corner about the traveling salesman's formula. What we are going to do is, since we start with vertex 1, so I will be 1 initially. And then S is the set of rest of the vertices. So 1 we have already considered. So rest of the vertices 2, 3, and 4. So it's a set of other vertices, remaining vertices. It's actually a subset of the set of vertices of the graph itself. Now this should be minimum of J, which belongs to S. Now J belongs to S means S is a set, 2, 3, and 4 vertices, set of vertices. So J belongs to any of these vertices. So within the equation we are now considering I as the first vertex. So over here beside, just below the adjacency matrix, I'm just trying to create a tree of how the path can be accomplished. Now J starts from 2 because each J has to be taken. J belongs to 2, the set 2, 3, 4. So first we consider J as 2. Now, so what this means is, from 1, we are proceeding to vertex 2. So this will be, the first part will be C of 1 comma 2 because I is 1, J is 2. So cost of this edge, 1 comma 2. That we can get it from the cost adjacency matrix. Plus G of J. What is J now? 2. And comma S. S is 2, 3, 4 at this instance minus the vertex which we have considered. So what actually this means, that is G of 2 comma and S minus J, what this means is, or S minus 2, what this means is, we are trying to find the cost from vertex 1 to vertex 2. We know that cost. And we are trying to find the cost from vertex 1 to vertex 2 plus the cost from vertex 2 to other vertices. Other vertices will be 2, 3, and 4 minus 2, which will give us 3 and 4. So cost of other vertices, that is 3 and 4. Now then, that is one thing. Then even 3 is adjacent to vertex 1. So J will now become 3. That is vertex 3. So here you can find we have J is vertex 3. So now what we do is we have to find, this is comma, because minimum we have to find, minimum between 3 J vertices. So cost of 1 comma 3, because now J is 3, plus G of, this is 3, that is J, and S is 2, 3, 4 set minus J, which will be 3, vertex 3. Then similarly, we have to do it for vertex 4. So for vertex 4, we have the cost from vertex 1 as C14 plus G of 4, that is J, and set S 2, 3, 4 minus 4, that is the vertex 4. So if you look at this tree, we are trying to, now we have from vertex 1 we can move to vertex 2, vertex 3, and vertex 4. Now what we do is, with this equation, we try to find which path, either taking from vertex, going from vertex 1 to vertex 2 or vertex 1 to vertex 3 or vertex 1 to vertex 4, which one is minimum. Now we will, let us just try to simplify this equation. So what happens now is, it becomes C of 1 comma 2 plus G of 2 comma, this is set difference. So 2, 3, 4 minus 2 is nothing but 3, 4. That is 3, 4. The same way, C1, 1, 3 plus cost of 1 to 3 plus 3 comma, this difference of this set, that is 2 comma 4. And then C1, 4 plus G of 4. And then we have 2, 3, 4 minus 4, that is difference. So we get 2, 3. So at this stage, we have only derived a condition, derived an equation through which we can find a minimum cost, which path, if we go to start from vertex 1, if we go to vertex 2 or vertex 3, vertex 4, which one will lead us to minimum. But we still don't know, because G of 2 comma set 3, 4 has to be computed. The same way, G of 3 comma 2, 4 has to be computed, as well as G of 4 comma 2, 3 has to be computed. So we will, that's the next stage. So this stage we have only derived the formula. Now we have to move on to the next stage. The next stage means we have to now find G of 2 comma 3, 4. So we'll first consider this part, G of 2 comma 3, 4. So S now is 3, 4. So S will be a subset now of the previous set. So J, nothing but the vertex J should belong to 3, 4. That is, now we know the cost from 1 to 2. But now from 2 to rest of the vertices, we are trying to find which one will lead us to minimum path. So that is why the set we have, the S set we have vertices 3 and 4, because that's the only two vertices which are left in this graph. So we start with I as 2, then J as 3 first, the first step. So we are now moving from, if you look at this tree, 1 to 2 we already had. Now from 2, we are moving to 3. So the cost will be Ij, that is this formula, the actual formula, Ij, that is 2, 3, plus G of 3, because J is 3, and the set S is 3, 4, minus J, which is 3. Then J will be 4, that is the next vertex. So we have trying to find minimum from going from 2 to 3, or which one will be minimum from 2 to 3 or 2 to 4. That is 2 to 4 vertex. So we have cost of C24 plus G of 4, that is J is 4 now, and set 3, 4 minus 4. So this reduces to cost 2, 3 plus G of 3, and then this is a set difference which will give us set 4, that is the only vertex now remaining to be visited. Then C of 2, 4 for the other part of the equation, G of 4, then the set difference, that is we get 3 as the only vertex. So again we have now we have just found from 2 which one should lead us to vertex 3 or vertex 4, which one is minimum, but we still don't know. So let us move further. Now the next thing is we have to find the simplify this G of 3 comma 2, 4. So that is, we know we can move from 1 to 3. Then we are trying to find from 3, that is now I will be 3, vertex I will be 3. From 3 we can move to 2, or we can move to 4. So set S is now 2, 4. So when I is 3, and at first instance J will be 2. So the cost is 3 to 2, the edge cost of the edge 3, 2 plus G of 2, and the set 2, 4 minus 2. Then now J becomes 4. So we are trying from 3 we compute the cost to move to vertex 4. So that will be C of 3, 4, that is the cost of the S3, 4 plus G of 4 and 2, 4, that is the set S minus 4. So now if we simplify this equation, what we get is G of 2, 3 plus G of 2 and the set 4. That's the only vertex we have to visit now. In the same way, we have cost 3, 4 plus G of 4 and the difference of the set. So we get the set as 2 with only one element. Now similarly, what we do is we find G of 4 and the set S, which is 2, 3 now, because from 4 we can move to either 2 or we can move to vertex 3. So I is 4 and we consider J as 2 at the first instance, and then we will compute the the cost of H42 plus G of 2 because J is 2 and the set 2, 3, that is S minus 2. In the same way, we consider now J as 3 and compute from 4 to the cost from 4 to 3, that is H43 plus G of J is 3 now and set 2, 3 minus 3, set 3. So this gives us, once we simplify, this gives us the cost from which one should be minimum, from 4 to 2 or from 4 to 3. So we have, once we simplify this equation, we have the the equations. Still, here we have 3 more values of G that has to be computed. 6 more values of G that has to be computed. So we still don't know the cost. We only know the cost of 2, 3 or 3, 4, 3, 2 or 4, 2. But we don't know these G values. So we'll proceed further. And then now again we will compute the similar fashion G of 3 comma 4. Now this 4 which is said is nothing but says that we can move from 1 to 2, 2 to 3, then from 3 to 4. 3 to 4. So I will be 3 and the set S will contain only one element now, 4. That is the that is what is left because we visited on the path the rest of the other vertices and that's the only vertex left. So it will be cost of 3, 4 edge, that is the edge between 3 to 4 plus G of 4 because J is 4 now and S is 4 minus J. J is also 4. So this will reduce to cost of 3, 4 plus G of 4 comma difference of these two sets will be a null set. In the same fashion, we will now compute going from G for G4, that is G of 4, that is vertex 4, to moving to vertex 3. Now this will be cost of 3, 4 plus G of 3 comma set 3 minus 3, which will give us C3, 4, the cost 4, 3 plus G of 3 and null. Null means there is no other vertex left now for us to move further. So in the same way, we have to now compute from vertex 2 to vertex 4. So I'll just go through these calculate the same similar computations that has to be performed. Same way we have to move to and compute for 4, 2. Yeah. So ultimately, what happens is so now, okay, one more thing is left out, that is 3 to 2. So now ultimately, what is left is we need to compute G of 4 and the null set null set obviously means there is no other vertex left to be computed. So now this G of 4 comma null, here we have null. So null, I said that there is no vertex left. So when in the sequence we have visited all the vertices, now from the last vertex, what should happen? We have to go back to the start vertex. As in the case of a postman, once he delivers all the letters, from the last house he goes back to the post office. So G of 4 comma null means from vertex 4 we have to go back to vertex 1. So going back to vertex 1 means from 4, vertex 4, how much is the cost? The cost is the same as the cost of that edge and nothing else. So G of 4 comma null will be C of 4, 1, which is from the adjacency matrix. We know that 4th row and column 1 will contain that cost, which is 8 in this case. Now this way we will compute for 3 to null. That will be, since start vertex is 1 over here, so that will be 3 to 1. That is the cost of the edge from 3 to 1, which will be 6, which is 6 in this case. Then from 2 to null, or from 2 to 1, that is, in this case it is 5. Now once we have this, we are at the last stage. Now we have to resubstitute these values in the previous equations and ultimately find the cost. So now let us substitute in this first one G3 or 3 comma 4, which will give us the cost as 3, 4. Cost of 3, 4 is 12. This cost 12 plus what we have is plus G of 4 comma null, which is 8. So we get, I mean, here actually there is only one element in set J. So there is, I mean, minimum is that value itself. So in this case it is 20. Then the same way 4 to 3, which will be cost 4 to 3. In this case it is 9 plus G of 3 and null, which is 6 in this case. So what we have here is we have the value as 15. Then the same way from 2 to 4, so cost of the S2 to 4 is 10. So 10 plus what we have here is G4 comma null, which is 8. So that will be 80. Then we'll compute G of 4 comma 2. So that will be cost of 4 comma 2, which is 8 in this case. And that plus what we have is we have G of 2 comma null, which is 5. So it will be 30. Then same way 2 to 3, we have the cost of 2, 3, which is 9 in this case, plus G of 3, 4 of 3 comma null, which is 6 in this case. So we have the value as 15. Then the last thing in this stage is G of 3 to 2, which will be cost 3, 2, and cost 3, 2 is 13. That is the cost of the edge from vertex 3 to vertex 2, plus G of 2 null, which is nothing but in this case it is 5. So we get the value as 18. So now we have computed these values. We will substitute these values in the previous equation. Now for the previous equation, what we have is minimum of cost of 2, 3, which is 9, plus cost of G 3, 4. And 3, 4, we have the cost as 20. So it's 9 plus 20. Then since J has two vertices to explore, that is 3 comma 4. So for 3 we have 9 plus 20, which is 29. And for vertex 4, we have the cost as 2 to 4, which is 10, plus the cost from of G, that is plus G 4 to 3, that is in this case 15. So minimum of these two. Now we have to, because J was, the problem was J was a set which, the vertex which belongs to set 3 and 4. So here what we are trying to do is we are trying to find the minimum cost from vertex 2 to vertex 3, or which one is minimum, from vertex 2 to vertex 3 or from vertex 2 to vertex 4. So here in this case 29, 25, here 25 is minimum. Then similarly we find the cost from 3 to 2 plus G of 3, 4, which is 18. So this is 13 plus 18. Then the second vertex is vertex 4. So cost of 3 to 4 plus 4, 2. So what we are trying to find here is which one has the minimum cost, whether it is from vertex 3 to vertex 2 or from vertex 2 to, or from vertex 3 to vertex 4. In this case it is 25, which is from vertex 3 to vertex 4. Then similarly we substitute in the equation, which is cost of 4 to 2. Here 4 to 2 is the cost of the edge from 4 to 2 is 8 plus the G of 2 to 3 or 2, 3, which is 15. So 8 plus 15 will give the cost from moving from vertex 4 to vertex 2. And then from moving from vertex 4 to vertex 3, we have cost of 4 to 3, that is 9 plus G of 3, 2, which is in this case 18. So we have 9 plus 18. So in this case 8 plus 15 is 23 and 9 plus 18 is 27. So the minimum cost is 23, which we got from moving from vertex 4 to vertex 2. Now these values has to be substituted in the previous equation. So ultimately we have reached the initial equation from where we started. So this is the cost of moving from vertex 1 to vertex 2, which is C of 1, 2. So we get this cost is 10 we have plus G of 2, 3, 4, which is 25. And that is the minimum cost from vertex 1 to 3, which is 15 plus we have G of 3, 2 to 4 or 2, 4, which is 25 again, plus the cost from vertex 1 to vertex 4, that is 20 plus G of 4, 2 and 3, which is 23 in this case. So what we get is we have 3 values here. That is the cost from moving from vertex 1 to vertex 2, or moving from vertex 1 to vertex 3, or moving from vertex 1 to vertex 4. So in this case, if you see, this cost is less because 15 plus 25 is 40, and this is 43, and here we have 35. 10 plus 25 is 35. So finally we got the answer is 35. This is the minimum cost of the traveling salesperson's problem. So we got the minimum cost as 35. Now let us trace the path it has to take, or which vertices the traveling salesperson has to visit, so that we get this cost 35 as minimum. Now we start with this, the initial equation itself. That is moving from 1 to 2 or vertex 3 or vertex 4. Now, which one gave us the minimum value? It is vertex 2. The jth vertex, which is vertex 2, gave us the minimum value. So starting from vertex 1, we move to vertex 2. Then in the next stage, that is from vertex 2, obviously we have now 3 things from vertex 2, vertex 3 to vertex 4. Which one should we move? So we cannot take anything. From 1 we move to vertex 2. So we have to consider G of 2, 3, 4, because from 2 we have to move to 3 or either 3 or either vertex 4. So the cost of this was 25. We got 25 from by the values 10 plus 15, which is nothing but moving from vertex 2 to vertex 4. That is C of 2 comma 4 plus G of 4 of 4 comma 3. So we move to vertex, from vertex 2 we move to vertex 4, not vertex 3. Then now from vertex 4 we have to look. So there are 6 equations here. We have to select from vertex 4. Now there are 2 equations, vertex 4 to vertex 3 and vertex 4 to vertex 2. So which one should we select? We cannot select vertex 4 to vertex 2 because vertex 2 we have already visited. So only other thing we have to look at is from visiting vertex 4 to vertex 3. That is what even in the previous equation we got that as the from that we got the minimum value. So obviously we have to move from vertex 4 to vertex 3. So this is the value we got from moving from vertex to vertex 4 to vertex 3. Now here J value is only one, that is set contains only one set, that is 3. So we move to 3, and then this we got it by adding G of the costs from the graph 3 to null. Now 3 to null means what? Means moving from vertex 3 moving back to vertex 1. So this is the path a traveling salesperson should take for this graph, which that is from starting from vertex 1, visit vertex 2, then visit vertex 4, then visit vertex 3, and ultimately come back to vertex 1. And the cost of this, that is the minimum or optimal cost, is 35. So this is how traveling salesperson problem is computed. You have to be, you need to remember this equation, that is G of I comma S, where I is a vertex and S is a set of vertices that are supposed to be visited from vertex I, or that can be visited from vertex I, which is minimum of Ci comma j, where j belongs to set S, that is j is a set, j is a vertex in the set S. So for each vertex in set S, we have to find the minimum value, that is cost of ij plus g of j and set S minus j. So that is the equation you have to remember. So this was the traveling salesperson problem.